Hi, my name is Ray, and I'll be talking about hardness of approximate diameter, now for undirected graphs. And this is joint work with Mina and Virginia. So the diameter of a graph is the maximum shortest path distance between two vertices. Here's an example graph with diameter 2. We're interested in how well can we compute or approximate the diameter of a graph. We'll use standard graph algorithm notation where n is the number of vertices, m is the number of edges. And today, all of our runtimes are only going to be in terms of m, the number of edges. And you can think of this as we're dealing with runtimes in the size of the input, or we're working with sparse graphs, so the number of edges is near linear in the number of vertices. For simplicity in this talk, assume all graphs are unweighted. This just simplifies the story a bit, and all our results, which hold for unweighted graphs, will also hold for weighted graphs. Today, a distinction that's a little more significant is by default, assume all graphs are undirected. So all undirected graphs can be made directed by replacing every edge with two directed edges. So computing diameter in directed graphs is a more general problem. It's harder to find algorithms, easier to prove lower bounds. So for undirected graphs, it's harder to prove lower bounds. And that's what we're going to do today. We're going to prove lower bounds in the harder setting. So computing the diameter is both of theoretical and practical interest. Theoretically, the diameter is a central graph parameter, and practically it's a useful measure of the connectedness of a graph. So a common example is the 6 degrees of separation phenomenon, which asserts that the diameter of some social graph is 6. And here's a list of other applications. So how fast and how well can we compute or approximate the diameter? So if we want an exact algorithm, so we want to compute the diameter exactly, one solution is you just compute the distance between every pair of vertices and you return the largest one. This solves something called the all pair shortest path problem, and it runs in quadratic time because you can run Dijkstra or BFS from every vertex, and that gives you all the distances. This takes quadratic time. It's faster if the graph is dense, but remember our runtimes are only in n, the number of edges. So this is the best known exact algorithm. And we can ask what happens if we allow approximation. There's a simple 2 approximation in near linear time, and I'll describe it here. So the algorithm is you pick an arbitrary vertex v, and you compute the distance from v to every other vertex, and you return the largest one. This obviously takes linear time, and I claim it's a 2 approximation. The proof is simple. If the diameter is d, there's 2 vertices a and b at distance d, so by the triangle inequality, your vertex v is distance at least d over 2 from one of them. So looking forward, the main result of our work is that assuming something called SETH, this 2 approximation is optimal. So there's no better than 2 approximation of the diameter in near linear time. So the best approximation ratio for near linear time algorithms is 2. Okay, but before we talk about that, let's keep talking about algorithms. So I'll put everything on this plot, which you'll see again. So on the horizontal axis, we have the approximation ratio. On the vertical axis, we have the runtime exponent. And we want faster algorithms, smaller approximation ratio, so better algorithms are down and to the left. We saw there's an exact algorithm in quadratic time and a 2 approximation in near linear time. There is also a 1.5 approximation in m to the 1.5 time. And lastly, there is an almost 2 to the minus k approximation in m to the 1 plus 1 over k plus 1 time. 2 notes about the last result. It only works for undirected graphs. The other algorithms also work in directed graphs, but this one is only undirected. And also this last result is an almost approximation, which means it not only loses a multiplicative factor, but also a small additive factor. So these are the best known algorithms for diameter. More is known if you assume the graph is planar or something, but for unstructured graphs, these are the best known algorithms, and the natural question is, are these algorithms the best possible? And one particular question you could ask is, can you get a better near linear time approximation? Can you get a better than 2 approximation in near linear time? And as I mentioned on the previous slide, the punchline of our work is no, you cannot, assuming this hypothesis set. So as you've probably figured out by now, our work is proving lower bounds. And how do you prove lower bounds like the ones we're looking for? We use something called fine-grained complexity. So fine-grained complexity, so in classical complexity, you've got these complexity classes, and you classify problems by how efficiently you can solve them, and you can make statements like if p is not equal to np, then 3 coloring cannot be solved in polynomial time. But today we're not looking at distinctions between polynomial time and super polynomial time. We're looking at more fine-grained distinctions, such as between linear and quadratic time, and that's where fine-grained complexity comes in. And it'll allow us to make statements like, if some hypothesis is true, then diameter cannot be solved in truly subquadratic time. The most popular hypotheses in fine-grained complexity are SETH, three-sum, and all pair shortest paths, and today we're going to be working with SETH hardness results. Just for some more context, so in your complexity class, you probably remember proving statements like this with reductions, and in fine-grained complexity, we're also going to prove reductions. Technically, they're different kinds of reductions, but it's the same concept. So fine-grained complexity is this very exciting field. The list of problems for which you have lower bounds literally goes off the page, and you can see Virginia's survey for more information. So today, we're looking at hardness results based on SETH and another hypothesis, OV. So SETH stands for the strong exponential time hypothesis, and it states that for all epsilon, there exists a case such that ksat needs 2 to the n times 1 minus epsilon time. So recall ksat is you're given a KCNF formula, an AND of ORs where every OR has k variables, and you want to know if there's a satisfying assignment. A trivial algorithm is you try every possible assignment. This takes 2 to the n time, and SETH states that this is essentially the best you can do as k gets larger. So SETH is much stronger than p not equal to np. P not equal to np hypothesizes that ksat needs super polynomial time. SETH hypothesizes that it not just needs super polynomial time, not just exponential time, but exponential time approaching the trivial bound. So that's SETH, and most hardness results based on SETH go through a hypothesis called OV. So the KOV problem, think k is 2 or 3 or some small constant, is you're given a set of n vectors of dimension d, think d is log n. You want to determine if there exists k vectors that are mutually orthogonal. So in every coordinate, at least one of the vectors is 0. And a trivial algorithm for this is you try all n choose k tuples of vectors, and you see if any of them work. And this takes n to the k time, and the KOV hypothesis says this is essentially the best you can do. And a classic result of Williams says that SETH implies the KOV hypothesis. So now to prove lower bounds based on SETH, we just need to prove lower bounds based on KOV. So now that we've defined SETH, we can talk about our results, which are hardness results under SETH. So remember, our question is, can we get a better than 2 approximation in near linear time? The first result in this direction showed a hardness that a better than 1.5 approximation needs 2 quadratic time. This is the first result that showed that an exact algorithm, in fact, needs quadratic time. So the exact algorithm that runs all pair shortest paths in quadratic time is optimal, at least in sparse graphs. And in terms of hardness of approximation, this gives a hardness of better than 3/2 approximation, especially in near linear time. This approximation ratio was improved to better than 5/3. A better than 5/3 approximation needs m to the 3/2 time, and then it was improved to showing a better than 7/4 approximation needs m to the 4/3 time. And our work kind of generalizes all of these and proves that a 2 minus 1 over k minus epsilon approximation needs m to the k over k minus 1 time. Previously this trade-off was known for k equals 2, 3, and 4, and we proved it for all k. And this in particular answers the question, if you set for any 2 minus delta, if you take k large enough, epsilon small enough, then we show that a 2 minus delta approximation needs strictly superlinear time. So we give a complete answer to this question. Previously, a partial answer was known. It was known that you could not beat a 2 approximation in near linear time for diameter in directed graphs. So in fact, these 2 concurrent results prove the same trade-off that we proved for undirected graphs by proving it in directed graphs. So we prove a trade-off for undirected graphs. Previously, it was known for directed graphs. And while superficially the results are very similar, proving the lower bound for undirected graphs seems to be much more difficult. I mean, certainly it's a more general lower bound, it's a harder lower bound to prove, but it seems significantly harder and seems to use new ideas. You cannot prove it just by somehow undirecting the lower bound for directed graphs. So the remaining question is, can you find better algorithms? So in this picture, the red region, the red trade-offs are not obtainable under SETH. The blue regions are obtainable by algorithms, but there's this white region of, are there algorithms, are there no algorithms, and so can you find better algorithms there? Okay, so now that I've told you about our results, I'll tell you about some of the techniques. So I'll illustrate the techniques by proving this first result that a better than 1.5 approximation needs quadratic time. In particular, an exact algorithm for diameter needs quadratic time. So the proof idea is we start with a size n 2OV instance and we turn it into a size roughly n diameter instance such that the following two things hold. If the OV instance has a solution, then the diameter is 3, and if there is no solution, the diameter is 2. Okay, so why would this be enough? Let's suppose we've done this. Well, by the results of Williams, SETH implies that 2OV needs quadratic time, and that implies that distinguishing between diameter 3 and diameter 2 needs quadratic time, because if you could do it faster, then you could solve OV faster by passing to the diameter instance and then solving the diameter instance, and that gives you your OV solution. So 3 versus 2 diameter needs quadratic time, and therefore a better than 1.5 approximation needs quadratic time. Okay, so we've proved this up to the non-trivial part of actually constructing the graph. So how do you construct a graph? You start with your OV instance of n vectors. You create one vertex for every coordinate, so every element of D, and you also create one vertex for every vector. And you connect the vector to all the coordinates where the vector has a 1. So like so, and you do this for all the vectors, and this is the whole graph. So first, let's look at the second condition, that if there's no solution, then the diameter is 2. First, all the coordinate vertices are distance 2 to everything. And furthermore, if there's no solution, then for any two vector vertices, they're not orthogonal, so they have a 1 in common, which means in the graph they have a common neighbor, so you've got a path of length 2. On the other hand, if there is a solution, there's two vectors that are orthogonal, which means the vertices have no common neighbors, and therefore their distance is 3. So this shows hardness of a better than 1.5 approximation. To get larger approximation ratio hardness, instead of reducing from 2OV, we reduce from KOV. So for the better than 5/3 hardness, we reduce from 3OV. For the next one, we reduce from 4OV. And in general, we reduce from KOV. And that's how we get our general results. So again, the result is SETH implies that a better than 2 minus 1 over k minus epsilon approximation of diameter needs n to the k over k minus 1 time. So the strategy is we turn a size n KOV instance into a size roughly n to the k minus 1 diameter instance, such that if their OV instance has a solution, the diameter is 2k minus 1, and if there's no solution, the diameter is k. So if you plug this into machinery, SETH implies KOV needs n to the k minus 1, n to the k time, and by our construction, that means that distinguishing between diameter 2k minus 1 and k needs m to the k over k minus 1 time, because m is n to the k minus 1, and that implies that a better than 2 minus 1 over k approximation needs m to the k over k minus 1 time. Okay. So like in the previous case, the hard part is not just changing these numbers and plugging the machinery, but it's actually constructing the graph. And this for us is quite non-trivial, and I'll give you some taste of it on the next slide. So now I'll illustrate the construction with k equals 5. So we start with our OV instance and we want to produce a graph. This graph is going to have two primitives, stacks and coordinate arrays. So a stack is just a list of vectors of A. So here's a stack with 4 vectors, and a coordinate array is a list of coordinates, so elements of 1 to D. And coordinate arrays always have exactly k minus 1 coordinates. We also define what it means for a stack to satisfy a coordinate array. So it's some annoying to define thing, but it's just what this picture shows. So the bottom vector of the stack has to have a 1 in all the coordinates. The next one has to have a 1 in all but one of the coordinates. The next one has to have a 1 in all but two of the coordinates, and so on. And furthermore, the coordinates where you've got 1s has to have this inclusion relationship as shown. And then in the other coordinates, you can have either 0s or 1s. So with these definitions, we can define our graph. So the vertices have are configurations of stacks and coordinate arrays. So here's a vertex with 1 stack. Here's a vertex with 2 stacks and 1 coordinate array. And we define what it means for a vertex to be valid. It's valid if certain stacks satisfy certain coordinate arrays. It's too technical to define here, but this is roughly the idea. Edges can be seen as operating on these configurations of stacks and coordinate arrays. So if you cross this edge, then you can see it as inserting the stack S prime and deleting vector A4. You can also have edges that, for example, insert a vector and then delete another vector. Okay, so at a high level, this is how our graph is defined, and it's similar to prior hardness results that don't use the stack and coordinate array language, but use it implicitly. In those constructions, they only handle at most 2 stacks and at most 1 coordinate array in any configuration. But we have to handle sort of what makes our result work for undirected graphs is that we need to handle more than 2 stacks and many coordinate arrays. And doing this makes it technically more complicated, but it makes it work for undirected graphs. Just to give you an idea of why these stacks and coordinate arrays help, I'll tell you about 2 concrete lemmas that these stacks and coordinate arrays satisfy. And these 2 lemmas are going to help us in sort of the no case and the yes case respectively, where we're trying to show the diameter is small and then in the other case the diameter is large. So the no case lemma says that if you've got 2 stacks S and S prime like so, and no 5 vectors among them are orthogonal, which is always going to be true in the no case, then they satisfy a common coordinate array. So I'll prove this by picture. So any 5 vectors always has a coordinate where they're all 1, so we can take x1 to be the ones where these are 1, x2 to be the ones where these are 1, and so on. And voila, you've got a common coordinate array satisfied by S and S prime. Okay, so why is this useful? Well, it comes up in finding short paths between pairs of vertices in the no case. So here's 2 vertices with 1 stack each, and we're going to sort of find a path that kind of performs these operations that transforms one vertex into the other vertex. And in doing so, we need these auxiliary coordinate arrays that need to be satisfied by kind of pairs of stacks in one vertex and the other vertex. And this no-case lemma is going to help us guarantee that these coordinate arrays always exist. So then we've got a valid path. Okay, so that's just sweeping a lot of details on the rug, but that's the intuition. Now, what about the yes case? So in the yes case, we also have a lemma, which states that if you have 2 stacks that satisfy a common coordinate array, so these 2 stacks satisfy this coordinate array, and they together have exactly 5, or in general k, vectors, then the vectors are not orthogonal. So here you've got 5 vectors between these 2 stacks, and indeed there's 1 coordinate where they're all 1. And this is true in general. Okay, so how does this one help us? Well, it helps us in the yes case where we assume that OV has a solution, so 5 vectors that are orthogonal, and we show that there's these 2 vertices that are distance at least 9. So the 2 vertices each have 1 stack, one of them has A1 to A4, the other one has A5 down to A2. And so we assume, for sake of contradiction, that there's a short path length at most 8 between them. We use this path, we find along this path 2 vertices that each have some stack, so S and S prime. S has, together they have all the elements of A1 to A5, and furthermore, there's some coordinate array in each of these 2 vertices that is satisfied by the corresponding stack. So that means that there's these 2 stacks that satisfy the same coordinate array, which means A1 to A5 are not orthogonal, and that's a contradiction. Okay. So this is just a high-level overview. If you want to learn more, you can read our paper. Now, just to wrap up, we start by talking about diameter algorithms. We talk about how there's a near linear time 2 approximation, and our punchline is that under SETH, this 2 approximation is tight. There's no near linear time better than 2 approximation. We talk about some of the ideas. We reduce from orthogonal vectors, and we have these new ideas from formalizing these stacks and coordinate arrays. That's all. Thanks for your time.